The Pennsylvanian period of the Paleozoic era. Rocks of this age are fairly common in Arizona, including in the Grand Canyon. As you can see here, the South Kaibab Trail descending down through the Supai Group. These cliffs and slopes of red rock here are all part of the Pennsylvanian, and the very top is Permian. That's the Supai Group, made up of 4 different rock formations. And then it'll slowly descend down through the Mississippian Redwall limestone cliffs here on its way down eventually to the Inner Gorge and Phantom Ranch. These rocks record a time of vast proliferation of land plants, swamps and forests spreading over the land surfaces, much like these seed ferns and spore ferns that are what will be called coal forests. And eventually this organic material will be transformed into various types of hydrocarbon deposits like coal and natural gas and oil. The Pennsylvanian period stretches from 323 to 299, roughly 24 million years of the Paleozoic era. Here we can see the Pennsylvanian on the ICS time chart, the lower, middle, and upper section, and it's following the Mississippian. This time term is used in North America, but most of the rest of the world uses Carboniferous. Both the Mississippian and Pennsylvanian periods are part of what's called the Carboniferous. In other places around the world, they call the Mississippian the early Carboniferous, and the Pennsylvanian is the late Carboniferous. The period itself gets its name in North America from Pennsylvania, where rocks of this age are exposed. From Philadelphia to Pittsburgh, you cross the Appalachian Mountain Belt from little towns like Bethlehem, Pennsylvania, all the way across towards Johnstown and Pittsburgh. You'll go through all the different areas of the Appalachian Mountains, and the Allegheny Plateau out here, these are all rocks of Pennsylvanian age. That's the light blue color. The geography of the Pennsylvanian period is dominated by the supercontinent Pangaea, which is the latest supercontinent in the tectonic cycle, spanning from South Pole almost to the North Pole. Siberia will be in collision with the rest of what was Euramerica here to fully form Pangaea. We're not going to talk in terms of Euramerica anymore. The northern part of Pangaea is called Laurasia, the combination of the Asian cratons and Laurentia. And the southern part of Pangaea is still Gondwana. The dividing line is really the suture zone in between, and that's where the Alleghenian highlands are formed, what are now the Appalachian Mountains. So that really subdivides the northern part of Pangaea from the southern part. These mountains are formed from the continent-continent collision of these supercratons. The Alleghenian highlands probably represent one of the biggest mountain ranges Earth has ever seen. This is a major continent-continent collision. The Ural Mountains formed at this time as well, with the collision of Siberia with the rest of Pangaea. The Paleotethys Ocean is still present out here, as is Anthalassa off to the west. You can see in the south, Pangaea has much of it is in southern latitudes, including the South Pole, so the buildup of ice there can continue, and so we'll see the ice come and go, and as a result, sea levels will fluctuate during the Pennsylvanian. And this is a map showing where the different cratons of Pangaea are located and the extent of the ice. Looking again at Ron Blakey's Paleo Globes, one showing Pangaea, again stretching from South Pole just about to the North Pole, if we include everything here. And here's the newly formed Alleghenian highlands, and this mountain belt stretches east to west right along the equator. The Earth has seen nothing like this before, probably, or since. On the other side of the planet, the Great Jaw, more or less, around the Paleotethys Ocean, and this jaw is going to be closing. Various subduction zones cause the destruction of this oceanic crust and the closing of this ocean basin. So this is what we think the planet looked like about 300 million years ago. Well, let's look at the geography of Laurasia, or northern Pangaea. Here we have Pangaea, and here are the Alleghanian Highlands. And they're a good reference point because they're more or less an east-west trending mountain range. Southern Pangaea is down here, northern Pangaea is here. This would be pretty much the equator. Laurasia is the northern part, north of the Alleghanian Highlands. Off to the west here, we have Arizona, and there's all sorts of different depositional environments going on during the Pennsylvanian, from different continental deposits, rivers, streams, even deserts, shallow marine deposits, a varied environment in the southwestern part of Laurasia. Much of Laurasia, though, is a broad continental plain, fairly featureless, more or less isolated from any large bodies of water. This is about 315 million years ago during the early part of the Pennsylvanian. During the later part of the Pennsylvanian, about 300 million years ago, began the Alleghanian Highlands separating north and south Pangaea. Laurasia here, broad continental plain. The Alleghanian Highlands are widening and maturing. A broad area of deformation as this continent-continent collision continues. Encroachment of the ocean here on much of the western part of Laurasia. Still have the island arc off to the west. So this is the late Pennsylvanian, about 300 million years ago. So let's do the flip chart for the Pennsylvanian. Going back to early Pennsylvanian here, you can see on the western side of Laurasia, this island arc here, shallow seas encroaching onto the craton. The arc still there during the late Pennsylvanian, and these seas would transgress onto the craton. The mountain belt itself just starting to mature, widening here in length over time, so that by the late Pennsylvanian it's much longer in extent and much wider. Let's look at the western part of Laurasia during the Pennsylvanian. A varied geography. Pretty cool time, actually, in terms of the geography. We had the craton itself covered by shallow marine areas here in light blue. Various mountainous uplifts here, lowlands in Arizona, and then these island arc sequences here of the Antler Highlands, and then another one behind it with the Panthalassic Ocean off to the west. A whole bunch of different depositional environments, both continental and marine. From shallow marine here to foreland basin to deeper marine in the west. One notable feature here is the ancestral Rocky Mountains, and that's this area here. There's a couple of these long, linear, kind of northwest trending mountain ranges which appeared in the Pennsylvanian. And these were for the Rocky Mountains we know today. They grew and were uplifted and formed during the Pennsylvanian period. You can see the map here. They were highlands separated from each other by very narrow, shallow seaways. This is a map reconstruction of the state of Colorado. You can see the boundaries there. Colorado Springs would be right about here. These are linear mountainous uplifts separated by these narrow seaways. This is a reconstruction of one of these areas right at the margin there, showing the mountainous areas and the braided streams coming off. These two different island uplifts had names. One was called Front Rangia, and the other one was called Uncompahgre. Front Rangia and Uncompahgre were the two main ancestral Rocky Mountain uplifts. Tectonics of the Pennsylvanian are dominated by the formation of Pangaea. Various supercratons coming together and forming Pangaea, Earth's latest and probably largest supercontinent. whether it's Siberia or Euramerica or Gondwana, they're all together now at their margins, suturing together to form continent-continent collisions in mountain ranges. That's what these orange lines are. The Alleghanian orogeny, the Ural orogeny, those are major orogenic events that occurred because of these continent-continent collisions. Alleghanian orogeny is the one that resulted from the collision of Euramerica with Gondwana. The Alleghanian highlands are the manifestation of that, this east-west trending mountain range that divides the supercontinent Pangaea itself into northern and southern halves. This is really the Appalachian Mountains that we know of today. The Alleghanian highlands is what we would have called them back in the Pennsylvanian. This is what is now called the Appalachians, and the Ural Mountains in Eurasia were formed at the same time. So let's focus on the tectonics of the central part of Pangaea, and that would be the Alleghanian orogeny, which began in the latest part of the Mississippian period and continued through the end of the Paleozoic era itself to the latest part of the Permian period. This is a continent-continent collision between Euramerica and Gondwana, and in this series of cross-sections, eventually the coming together of Pangaea itself. So from the Precambrian, the rifting of Panotia, that previous supercontinent, and then the Taconic Island arc and its accretion onto Laurentia, and then the Avallonian microcontinent and its accretion onto Laurentia to form Euramerica, and then finally the collision of Gondwana with Euramerica to form Pangaea, a true continent-continent collision. That's where we are in the Pennsylvanian. So this is the third orogenic event in the formation of the modern-day Appalachian Mountain Belt. Okay, the first was the Taconic orogeny, an island arc collision. The second was the Acadian orogeny with a microcontinent collision. And then the third is this full-blown continent-continent collision. This is really what formed the southern part of the Appalachians. The Taconic and Acadian orogenies formed much of the northern part of the Appalachians. The Alleghanian highlands occurred through the whole length of what is now the Appalachians, and the southern part is really what formed during this event. The Appalachians continue from Scandinavia through New England, down the mid-Atlantic states, through Alabama, Mississippi, into Texas. Of course, today, much of this has been covered by younger rocks. Mountains in Arkansas and southeastern Oklahoma are called the Ouachita Mountains, and this is one area where the Appalachian Mountains are actually exposed. Basically, the Appalachians continue here, and then you see them again in the Ouachitas, and then they're covered again. The Alleghanian orogeny includes abundant folds and thrust faults. A continent-continent collision is dominated by fold and thrust style deformation. A lot of horizontal tectonics with the compression giving you thrust faults like this, where the hanging wall is thrust up and over the footwall. The fault itself is fairly low angle. That's called a thrust fault, and there's usually one master fault and then a bunch of little ones. It's very complicated in that regard. Fold and thrust belts also include folds, so reverse faults and thrust faults and folds like anticlines and synclines are very common in these areas. And so here we can see a cross-section of the Appalachian Mountains where there are abundant thrust faults and folds as you go from east to west across this area. It's very common of most fold and thrust belts around the world. We see the same kind of structures, whether it's in Iran or in the Himalaya and other places. The Alps. Here's a road cut in Pennsylvania, broad folds, anticlines and synclines. Here's another large syncline in Maryland. So that would represent more or less this area of the mountain belt. Let's look at Western Laurasia and the ancestral Rockies. These are mostly Pennsylvanian and then early Permian uplifts and intervening basins in the middle of the craton here. So these linear mountain ranges, the ancestral Rockies. Okay, here's a map of them here between the Alleghanian Highlands to the southeast and the Antler Mountains off to the northwest. Several tectonic features on this map here. This map shows a similar area here of North America. Here's the continuation of the Alleghanian Highlands, the Ouachita Mountains. Then here are the ancestral Rockies with Uncompahgre and Front Rangia. And Sierra Grande is another one. New Mexico has its own names for these things. But these were the result of the collision of Euramerica with Gondwana. So this Alleghanian orogeny not only produced the Alleghanian Highlands, but the ancestral Rockies as well. And the idea is, as the supercratons came together, there's a lot of compressional stress, a lot of folding and thrust faulting, and the compression direction was like this, coming together, and that would mean that the tension direction is kind of at right angles to that. And if you have tensional stress, you can have normal faulting, and it's thought that behind this collision zone there were tensional stresses that allowed the creation of normal faults, which dropped basins down relative to the mountains. And that's what formed these uplifts. So it's kind of a secondary aspect to this collisional orogeny that you get this local area of extension and tensional stress, uplifts in basins. Some important rocks of the Pennsylvanian in Laurasia include cyclothems, and these are transgressive and regressive deposits that are caused by fluctuating sea levels. If we look at a depositional environment diagram here, you see non-marine deposition in streams and channels and floodplains feeding into the ocean, large swamps, marshes, river deltas, and then shallow marine deposition over here. With a marine transgression, sea level rises and the shoreline moves inland. In this biomass here, where a lot of the spore plant and seed plant vegetation is concentrated, would then get buried and eventually form a coal seam of the future. So sea level rises, the shoreline goes in, marine transgression, and then when sea level drops, the shoreline would move seaward. It's a marine regression. Well, we see this pattern, a strat section here from the Midwest in the U.S., and at the bottom, these rocks here represent the coal swamps and the river floodplains and deltas, near shore marine and non-marine deposits, and then overlying them are deeper water marine limestones, and then deeper marine shales. So shallow water rocks overlain by deeper water rocks, that's a marine transgression. That's followed by sea level dropping. When that happens, you have the shoreline moving seaward, and in the rock record we see that reflected by deeper water rocks overlain by more shallow water rocks. So we go from the deep marine shales back into the limestones, carbonate rocks, to the near shore deposits and even non-marine deposits including coal. So that's a marine regression. The transgression and regression here represent one cyclothem, and that cyclothem simply represents the rise and fall of sea level. And here you can see another one starting, and that's the second cyclothem. Again, fluctuation of sea level over long periods of time. Another important rock package is called a clastic wedge, and we talked about these before when we talked about the Taconic Highlands and the Acadian Highlands. Any mountain system is going to be subject to weathering and erosion, and then you'll get debris being shed off of those, and they'll collect in what we call a clastic wedge along their margins. And so in the Appalachians, we see a number of these clastic wedges of different ages. Some are related to the older Taconic Highlands. Some are related to the Acadian Highlands. Remember the Catskill Delta? And then some are related to the new Pennsylvanian Alleghanian Highlands. Okay, and these were some of the biggest ones yet. And so this accumulation of debris along this margin here gives you these clastic wedges. Many different rock formations included in this sequence. So typically thickest over here nearest the source in the mountains, and then they thin out as you go off to the northwest towards these basin areas. Let's talk a little bit more about these coal deposits, because these have major economic significance for us today. So off to the west of the Alleghanian Highlands, which would have trended from Texas all the way up through the Gulf Coast into New England, sediments were being shed onto coastal plains. You had a lot of vegetation in nearshore environments, like in the Allegheny Basin or in the Michigan Basin, Illinois Basin. Some of those basins would have filled up with sediment, and you could have had marshy environments and swampy environments. So we see a significant accumulation of coal in these areas. These are the coal beds that we mine today in Appalachia, stretching from West Virginia all the way to Illinois and to Michigan. The Katanning coal bed is a very important one in Pennsylvania area. So whether it's in eastern Pennsylvania or the broader deposits farther west, these are all exposed pretty much at the surface and then even in the subsurface. So there's a number of different coal layers. These are all Pennsylvanian units here, whether it's lower, middle, or upper Pennsylvanian in age. Pottsville, there's a major coal seam related to rocks of this age. The Alleghanian rocks, a number of different coal beds there, including the Katanning. The Conemaugh has two important ones, and so does the Monongahela. So all of these are Pennsylvanian in age, these different coal seams, representing deposition in these organic, rich, swampy, marshy environments. A little farther west in western Laurasia, we have the Supai group, which is a Pennsylvanian to even early Permian collection of rock formations, spanning a range from 323 down to about 290 million. These are sandstones and mudstones, mostly with some carbonate. They're deposited in a wide range of both fluvial floodplain kind of environments and also desert sand dune environments and also shallow marine. Remember, the area of Laurasia is dominated by the ancestral Rockies. So material being shed off these would be in alluvial fans, would be rivers and streams, floodplains, river deltas, shallow marine areas, sand deserts along the coasts, a whole range of different depositional environments, giving a whole range of different sedimentary rock types, including sandstone, which would represent the rivers and streams and shallow marines and even the desert sand dunes, mudstones and carbonates from the shallow marine environments, and also mudstones from the river floodplain environment. So here's the Supai viewed from along the South Kaibab Trail. And here's the South Kaibab Trail that winds its way around O'Neill Butte. This is the top of the Red Wall, which is Mississippian. Here's the contact with the Supai. And there's 4 rock formations that are present in the Supai, and 3 of them are Pennsylvanian, and the youngest one is actually Permian in age. So the Wattahamaji Formation, the Manakachaw, the West Kogami, and the Esplanade. Those are the 4 rock formations of the Supai group. Supai, it's easier to say that than these 4 names here. Another famous Pennsylvanian rock formation is the Fountain Formation, which is Pennsylvanian in age as well. And this is present in Colorado and places along the Front Range of the Rocky Mountains. From the Denver region all the way down towards Colorado Springs, we see these tilted layers called flat irons, and in some of those flat irons we see the Fountain Formation. This is Red Rocks, which is a cool amphitheater to see concerts and such, and you can see that it's built right in to the flat irons here on the Front Range of the Rockies, and the rock unit there is the Fountain Formation. And a closer look reveals it to be mostly conglomerate and sands that represent deposition along the edges of the ancestral Rocky Mountains. In this case, Front Rangia, and there would be Front Rangia, and here are the streams coming off, and you're getting fluvial stream deposition in channels and floodplains, giving you the Fountain Formation. So coarse grained material, meaning it's closer to the mountains rather than farther, but it's a very distinctive rock formation you see in Colorado. Climate of the Pennsylvanian includes the continuation of these Gondwana glaciations. In fact, it's pretty much dominated by these glacial cycles. So you'll have periods of cold, lower sea levels and periods of warmer or interglacials with higher sea levels. We are right here in the temperature cycle, fairly low with some fluctuations. The oxygen at the time is still rising, and it will continue to rise throughout the rest of the Pennsylvanian into the Permian. CO2 has dropped to its lowest level in Earth's history and will remain low into the Permian. Of note is the oxygen levels were as high as today or even higher. From the Pennsylvanian through the rest of the Paleozoic, oxygen levels would be even greater than they are today. Carbon dioxide, on the other hand, is about what it is today. So these extremely low levels that the Earth had never seen is what we actually have today. The climate is fluctuating during this ice age. Life during the Pennsylvanian included abundant insect life, including winged insects, some of which were very large. Meganeura, I think, is the biggest insect that ever lived, and it had a wingspan of about a meter or so huge flying bug, if you will. Here's Nigel holding an example of one of these. These insects really took advantage of the higher oxygen content in the atmosphere. So along with insects, we had amphibians continuing to be abundant and to enjoy the large swampy environments. This one here is called Fedexia strigeli, and it was actually unearthed at the FedEx depot at the Pittsburgh airport. That's the name. Let's look a little bit more closely at land life during the Pennsylvanian, specifically the vertebrates. We have the first reptiles appearing in the Pennsylvanian. Hylonomus here, a fairly small reptile, was the first unquestionable reptile in the rock record. When we look at the journey members of phylum Chordata have taken from the earliest chordate ancestor Pikaia into younger jawless fish, and then jawed fish, and then tetrapods, amphibians, and now reptiles. From that we'll see birds and mammals a little bit later. Reptiles are a little bit different than amphibians. Here's a cladogram for class Reptilia. These are different groups, and as we move this way on the cladogram, we're getting more and more shared characteristics. So all these are vertebrates. A fish is a vertebrate, amphibian's a vertebrate, a reptile's a vertebrate. This is class Reptilia, all these different groups here. Fish aren't tetrapods, but amphibians are, and so are reptiles. Reptiles are amniotes, but amphibians are not. And so an amniote is an organism that basically lays its eggs on land or carries the egg within the mother, whereas amphibians lay their eggs in the water like fish do. Amphibians are tetrapods, but they're not amniotes. Amniotes lay their eggs away from water, and reptiles are well suited for this because they have scales and they have a different internal makeup so that they can hold their water better than an amphibian can. So they can venture away from water sources farther and longer than amphibians, and thus they can lay their eggs away from the water. And this would give them a huge advantage in finding food, escaping predation, and all sorts of other things. Land plants during the Pennsylvanian were certainly abundant, including spore trees, ferns, sphenopsids, which are segmented, pretty easily recognizable, as well as seed ferns. So the mix of both spore plants and seed plants now in abundance would create very rich plant life during the Pennsylvanian. Various types of seed ferns, including Glossopteris and Gymnosperms. So when we look at the geologic age ranges, we can see the dominance of the spore plants early, and now we're in the Pennsylvanian. Seed ferns become very abundant, as do what are called chordaites, which are a type of gymnosperm, like the very earliest ancestors of pine trees, conifers. Typical recreation of a Pennsylvanian swamp showing the various ferns and scale trees. Some of the lycopod plants include Lepidodendron, and this is the typical scale tree of the Carboniferous or the Pennsylvanian. Its trunk had this scale-like pattern, very characteristic for Lepidodendron. These are huge trees, much like Archaeopteris, spore trees that are very high, broad canopy here, maybe up to 100 feet high. This is a a preserved lycopod forest. These are all trunks of lepidodendron that have been excavated. So these are the Pennsylvanian scale trees. Sphenopsids are segmented spore plants. They have a horizontal root, pretty simple, and then they grow off of this horizontal root and have a segmented trunk. Pretty distinctive looking. This shows how big they could have reached, several meters in height. We still have plants like this today in the form of horsetails. These are very ancient looking sphenopsids, still around today, but they are very abundant during the Pennsylvanian. Lastly, we have the appearance of gymnosperms, which are a type of seed plant that would become very important in later geologic history. Some other types of seed plants include cordaites, seed plant trees, and there are also cone-bearing seed plants, which include the conifers. The seed is protected in a cone like this, and so we see conifers going back all the way to the Pennsylvanian. Again, the advantage of a seed plant over a spore plant is that it can flourish in drier conditions, more extreme conditions. They can grow away from water sources and cover much more of the land.